All right, let's get started. Okay, so this is a chapter that I think has a lot of, at least two interesting models in it, particularly the fisheries model allows us to talk about some more complicated or complex things that can happen in these models, in these dynamical systems. So we start off with this urban growth and stagnation, which is kind of just a warm up for, I think, the rest of the chapter here. And this is focused on kind of a true story where if you look at cities, a lot of cities have this trajectory. They start small, they grow, they seem to kind of grow quickly at some points, and then they peter off. And so we've seen this time and time again. You know, this looks just like this typical S-shaped growth curve. So the common pattern and likely reflection of the structure of a city. So because you see it across so many cities, then that suggests that although maybe some details like why it's a little bumpier here than here, or why it kind of goes down to this level instead of going straight across here, you know, straight horizontal. For some reason, it's an easier time when I go from this direction. Why it doesn't go straight across and goes down. There's some things that are going to be specific to the city, but this general coarse grain pattern seems to be explained by potentially a general property of a simplistic city, which makes you think you could actually build a model that, even though it doesn't have all the details of London, would still maybe, so, you know, give you this. And so we want to sort of say, well, what are the underlying processes that might be working in concert to generate this pattern in cities? So what causes cities to stagnate in their growth? And so this question was of interest to Jay Forrester, kind of one of these founders of system dynamics modeling. And he got together with John Collins, who's a former mayor of Boston. And as universities like to do, they have big names. And so universities are all about prestige, right? So, you know, how do you get tuition dollars? You get higher up in US News and World Report. How do you get higher up in US News and World Report? Doesn't depend on how well I teach you. It's not like you guys report back to US News and World Report. It really is all about reputation. And so rather than seeing how well education's going on, the US News and World Report sends out surveys and says, you know, what universities do other administrators in universities recognize? And so they recognize people because of the people they hire. And so you end up hiring these people that maybe have no business being in a classroom, but you know, supposedly have good professional background, but in reality just prop up the university. And so that's what happened in the case of at MIT. Hire a mayor, why not? Mayor's available, he's got nothing else to do, may as well give him an office. And his office was down the hall with Jay Forrester. And so they would go out to lunch and they would talk about things like why cities do this. And so Forrester thought that was kind of interesting. And so he said, well, maybe this is a dynamic hypothesis that might explain what's going on. So what we mean by dynamic hypothesis is we're saying it's a possible observable processes working in concert to produce the pattern that we see. And so Forrester's saying, if we know enough parameters about the growth of a city, and we'll go through this, how the city ages and how attractive the city is, that those three together might be enough for us to generate this pattern. And if it doesn't generate this pattern, then we need something else. But if it does generate this pattern, then maybe that lends support that these are the main drivers of growth and stagnation in cities. So that's what they were shooting for there. And so we can zoom in on this and we'd say, well, it's a growth process. So what is the main engine of growth? So whenever you see an S-shaped growth you're trying to explain, you really want to focus on first, what are the feedbacks that there's got to be something that looks like exponential growth. And so the thought was here, well, if I have existing economic infrastructure, then that's going to lead to an expansion of infrastructure. And that expansion of infrastructure, after the time it takes to build it, will then produce new economic infrastructure. So the infrastructure, like businesses and things like that, will generate money for the city. As they get more money for the city, they'll reinvest in growing. And then that growth takes a little bit of a time. And so then behind it all, you see a growth of the city. And so this is when cities are small, this is how they get bigger. They take what they've got, they raise a lot of money, and they build more stuff. That's the thought here. But that can't go on forever. So there's got to be some limiting loop. The first limit that seems to be important is just land. So that new economic infrastructure, that generates, it goes into your total infrastructure, which is going to give you your total land area filled. But as you fill all your land up, it eventually reduces your ability to continue this process. So when you're small, this isn't really happening, but as you get large, then your expansion gets really costly to expand, or even impossible to expand. So this in itself might be enough to generate S-shaped growth. But what we might find is that a city peters off before they reach their land limit. And then we'd have to say, well, then what else could be going on? So if we just built this model and simulated it, we might get the right structure, but based on the models of cities we're building, like we built an approximate model of London, it might predict that London gets a lot bigger than it actually gets. So what other things could be limiting it? Well, there's things that are kind of related to the land limit that might need to be thrown in there. So the new economic infrastructure kind of becomes old after some time. And when it becomes old, it's just not as productive anymore. So, just look at the diversity of buildings on campus. It's interesting, some of our new buildings aren't necessarily all that they're cracked up to be, but still, there is a difference in the functionality of these buildings and where people want to go and things like that. And it certainly goes for a city as well, and so there's this aging process, and as things age, then that can reduce the effectiveness of this new economic infrastructure and in generating money for this growth loop. So there's that. And then, of course, the old infrastructure, that is adding to the total infrastructure. So the point here is, as new buildings become old, they don't open up space that allows new buildings to go in. You actually got to get rid of the new buildings. And so that's probably not going to easily happen. So this is definitely related to that. But it still seems like, that the growth of cities isn't just about the commerce going on in the cities, it's about people living in cities. So if we really want to explain the growth and petering out of cities, we need not only the stuff about infrastructure, but about the people. And so so that's kind of all the kind of land together. And then the people, that was this loop up here. And so the idea here is you're getting all this new infrastructure, it's going to attract people to your city. And as they come to your city, then they'll grow your population and everything. But as more and more people come there, after a certain amount of time, it might make the city less attractive. It's like the Yogi Berra effect, like nobody goes there anymore, it's too crowded. And so the idea here is as the attractiveness goes down, then the migration may go down, then that will end up reducing the growth in the population. And that may end up causing the city attractiveness to kind of peter out. That kind of, it was a really great place to live. Now it's just meh, or now it's really, nobody wants to live there anymore. So, and then the alternative cities is another. Right now it's modeled as an exogenous factor. It's a slider. So you just say that there's a fixed attractiveness. Now, in reality, there's another feedback loop here, which has to do with one city gets attractive, it's going to have competing cities trying to up their game so that people want to live there instead of in the neighboring city, and going back and forth, whatever. So you don't want to live in Tempe, so you live in Chandler or something like that. So all of those things could be going into it. So that was what Forrester and Collins thought was like a minimal working model for a city. If you had any one of these, or as long as you had the growth loop and any of these balancing loops, you probably could get that S-shaped growth. But to get something that matched the scale, the plausible relative scale of a real city, the claim was you need all of these things together. All right, so this is their basic model, is a causal loop diagram, and you got to populate the kind of stock and flow diagram. So this is what I say is a dynamic hypothesis. It's a possible answer to a research question, where our question is sort of what causes this pattern. So now, we had our sort of question about the cities. We now have our dynamic hypothesis characterized by the CLD. So this is the step you do in science. You always start with a question, go to hypothesis. The next is to say, if the hypothesis was true, what would the prediction be? And that prediction will give you an outcome that you can then measure. And that outcome that you're measuring, you can test in simulation to see if it kind of matches. So a lot of times in our case, the simulation really is the prediction, and then we're testing by comparing it to reality. So, so that's kind of what we're doing here, is that we have our hypothesis, we're gonna build a model, which will be our predictor. We're gonna run the model, and that will generate a prediction. And then we see, does the prediction match reality? If it doesn't, then that invalidates our hypothesis, tells us we have to go back to the drawing board, something else is going on here. If it matches, then it gives support that maybe these really are the minimal working things that go into what drive the city. So now to generate our prediction, we need to go deeper. We need to go behind the curtains and say that CLD isn't enough. And so this is when you go from your CLD that you kind of put in your proposal stage into the stock and flow model that you put in the actual final project. And we're going to look at each one of these different sort of sections here. So you can kind of notice there's sectors. So there's like an industry sector, a housing sector, and a population sector. And they all look similar. And so if we zoom in on any one of these, we'll see that they look kind of like an age-structured population. They don't look that different than like an SIR model or something like that, where the idea here is there's sort of a birth rate of, but it's not a birth rate of people, it's like a birth rate of enterprises. So there's a construction, a new enterprise construction. It says, how quickly are new enterprises coming into the city? And that, of course, is going to need, and we haven't added the coordinating network, that is going to maybe need to start high, but as the city grows, get lower because there's no ability to do the more construction. After some time constant, so this is again, just, it's like people getting well, they're sick and then they get well. So you model like how long does it take for a building to go from being new and fresh to kind of being old and outdated? Is it 10 years? Is it 20 years? That time constant goes into here, and then gradually things move into this middle compartment. And then they're mature. There's another time constant when they move into like declining industries, and then eventually they get demolished so that they can regenerate. But this overall, this is a giant kind of delay line that needs to happen before you can reclaim that land. So this is how we're modeling industry. It's just this age-structured population. And so there will be arrows coming into these things we just haven't drawn yet. But does this structure basically make sense to you? Could you see yourself coming up with something similar to this? You're just like, imagine you've got a model where things start in one state, after a little bit, they become in another state, after another little bit, they become in another state. If you feel things flowing like that, and you need to keep track of how many things are in each bin, then this is the type of model you want to build, this age-structured population, just like an SIR model, for example. It's all the same modeling fundamentals. So any questions about this? Does it seem like this makes sense why they chose this as a model for keeping track of the state of construction throughout a city? So at any instant, there's some new, there's some mature, there's some declining. Okay, so then we get a little more complex when we think about housing. So it's the same basic idea where we've got an age-structured population. The idea is the freshest, newest housing is premium housing. It will mature into housing that'll be available for people to make a little less income, worker housing. That will mature into housing that's maybe even cheaper for underemployed housing. Now, that's not the only way you get worker housing. Certainly, you have people building worker housing directly. So that's why we've got these additional flows coming in here. So there's two ways that we can get houses on the market for people who work there. Either they mature from what used to be premium housing, or they were built immediately as worker housing. Same thing for underemployed. You can have underemployed construction immediately, or it can mature from these other bins. It's still an age-structured population, but we've now added these like auxiliary birth rates, where now things can get born into these intermediate stages. But otherwise, it's the same process as it's above. Does that make sense? Any questions about that kind of structure? All right, so I like about these sectors is they kind of keep embellishing as they go from one sector to another. You can tell that Forrester had the same thought in mind for how they're going to model all these things, but he just kept kind of bolting on new things that specialize this. And so in the kind of like the fanciest version of this age-structured population, or age-structured population is the actual population. So here we imagine bidirectional flows. So we can have people, they can, they can arrive in this bin here of underemployed. And if they're underemployed, there's lots of different ways they can get there. They can arrive to the city from other cities. They can be born into the city, and then they can leave the city. Now, these underemployed might get promoted into a job, or they might lose their job. So now we have flows going back and forth. And so we need to model what's the churn from people up into work and down into unemployment. But then the workers, once they're there, there's a possibility that they will get promoted into managerial professionals. And in this model, they get stuck there as managerial professionals. So this is a pretty secure job. So these aren't secure jobs, and these are secure jobs. And so it's a ratcheting effect once you get up to here. Now, of course, people can immediately arrive, like they're in a family that they can immediately get a job. They can arrive from other cities. They can depart this city. Similarly with managerial professionals. And so we've got these additional flows coming in through here. But this is just further embellishing an age-structured model so that now, instead of things moving all in one direction, you've got arrivals and departures coming in at all levels, and you've got some bi-directional flows in between the boxes. It looks uglier, but if you've already gotten used to that sort of SIR type, one-directional flow, this isn't that different from it. So hopefully, as you're starting to look at these things, the complexity, you squint a little bit and some of the complexity fades away and you just see, an age-structured population. Okay. So any questions about that? Does this basic structure make sense? Or how they're modeling these different sectors of the city? Gesundheit. So this is the step you do. So this is basically when you're doing your final project, after you've come up with the dynamical variables, that's kind of causal diagram, you go to this step, you come up with your stocks and flows, you draw all those out. And then the next step is figuring out how to connect all those together. And that's where you get this coordinated network. And so in this diagram, they've summarized here, they've gotten rid of a lot of the flows that maybe don't have a lot of the cross connections, just for simplicity in the book. But they've left the stocks in there. So these are all the stocks that we saw on the previous slides. There's new enterprises, there's premium housing, there's managerial professionals. So imagine that there's flows here that just aren't being drawn just for simplicity. And what they're trying to focus in on here is that in order to figure out a lot of the variables, the flows on the other side here, it requires models that have to do with all of these variables. So to figure out how much, like for this underemployed arrivals. Well, for this underemployed arrivals, that's ultimately depending on this attractiveness mobility multiplier, which comes from all of these other variables, which have to do with how much business is available and how many people are there and how many people have got good jobs. So what this is modeling is that initially, if everybody's got a job, and all the businesses are new and fresh, then this attractiveness mobility multiplier is going to be high, and the underemployed arrivals are going to be high. And this is going to model how people arrive to the city. So imagine you're looking at your final project, you got all your stocks or whatever, and in order to focus on one flow, you kind of want to do this process. Forget all the other flows exist, but never forget the stocks exist. And then say, what stocks do I need to really figure out this flow? So what matters to people arriving to a city? And the claim here is that all of the dashed lines here matter to someone at some point when they arrive at a city. And then you come up with a model, and the model may not be, a mathematical formula that you can justify, but at least initially you come up with something that has the right shape. And the shape might be that if the multiplier, if say the number of new enterprises goes up, you want the multiplier to go up. And when the multiplier goes up, you want the arrivals to go up. So they at least have to move in the right direction. So you could explain that direction. And then you create these formulas and then do that for every single flow. That's how you kind of do this. This is a little more complex of a model than I'd expect for your final projects. Your final projects, some of you might get to this level of complexity, and that's great. But I think a lot of you will probably have 3-4 stocks maybe. then maybe not a lot of bidirectional flows, and that's totally fine. You can get a lot of cool stuff with just that. But this is just showing for a complex model like that, the process. It is just a step-by-step process of filling these things out. Okay, so that's basically how you get from the CLD, your hypothesis, to the simulation, which is a tool for generating predictions. So any questions about this process, how they went from sort of here to here? Again, I'm not, this isn't a class about cities. It's a class about if you were interested in cities, how would you come up with a model to help gain insights into cities? All right, so we generated this tool, now we generate the predictions. And so when we hit simulate on this, then your simulation tool comes up with a giant graph here, and it looks ugly because he's plotting a lot. And so they've got the premium housing, the new enterprises, et cetera. The key point here is that across all of these, you get this initial kind of exponential rise, and then they level off at different levels because they're different quantities, but they kind of level off exactly kind of as we were expecting. And then now we can look at this and we can see, do these patterns make sense? Does this roughly match the scale? When I say match the scale, a lot of you, I think, are simulating cities and you're very tempted to put in the actual population of Tempe or of Chandler or of wherever. And you could do that, but a lot of times the numbers will be so big that VinSim will start giving you errors, like it'll say floating point error and things like that, because as it starts trying to simulate the city, it just runs into the limits of what the computer can do. And so a lot of times you want to scale that down, either by using different units. So instead of modeling every person, you maybe model every 1,000 persons, or you scale things out and you say, imagine we are thinking of a city that's actually has 10,000 people in it instead of 1 million people in it. And a lot of times we'll get the exact same patterns. So you say, how much does scale matter? What's the smallest scale I can choose, which will make the simulations faster and easier, that can still capture the same patterns. So for the scale chosen, then we could evaluate, do these make sense? And if they do make sense, then we've got a good surrogate where we now can sort of understand if we wanted to extend this growth, is it more important, like what's kicking in first? Is it the land constraints that are kicking in? Is it the lack of attractiveness? And we can look at these curves and we can see kind of what is the leading indicator of this tapering off here. And we see like labor grows really fast and then it like seems to kind of collapse and then it bounces back and recovers or whatever. Is it this initial labor collapse, which doesn't seem, when I actually look, if I worker housing, it kind of collapses just before the labor collapse. So that kind of tells me that there's something going on with worker housing that maybe is preventing people from coming in. Is it, I could further go into this and say, maybe there's something about housing that is the initial indicator that we're gonna level off. And if I make sure that I have more worker housing, maybe I can extend this growth for longer. So maybe that's where I wanna put my priorities. So that's how we can kind of look at this. Like when you have a bunch of policy angles, a simulation like this can help figure out how to prioritize things to give you an idea of where it makes the most sense to put your money into trying to extend your city's growth. Because it may not be that you're limited by the things you think you're limited by. Okay. So any questions about, so this, I'm just putting up, this is our original, these are our data. This is our simulation. Realistic parameters, the scales are even similar. So that's kind of all good there. So any questions about this example? Questions online? All right, cool. So this was an example of a modeling approach. And so this approach is one where you start with a dynamic hypothesis, which is my answer to the question of basically how the heck, what's going on underneath here. And I then go and from my dynamic hypothesis, my causal loop diagram, I choose stocks and flows. And then I put those together and I choose a coordinating network. And that basically allows me to generate a whole simulation model. And then from that simulation model, I run it and I compare the simulation output, which are kind of a prediction based on those hypotheses, to reality. And if my predicted output from the simulation mismatches from reality, then we say we reject the hypothesis. And that means we need to go back to the drawing board, see what we did wrong there. See, maybe we needed to add something that we didn't have before. So that guides us in this process. All right, so questions about that general example of modeling cities with these dynamic models. My mouse over there, okay, good. All right, well, let's jump ahead then. So this next one, there's a lot of natural resource economists in the School of Sustainability. Everybody loves fisheries. Fisheries are a great model for natural resource problems, and they're just cool in general. So you see here a lot about fisheries, and this is starting to get into the cool complexity that goes on in a real fishery. So I like this kind of example. So we've started out building up like an onion, like adding layers to onion to this really simple natural fishery model. Hopefully everybody's familiar with this by now. You know, it's got this cool net regeneration thing, and that's really where all of the interesting dynamics happen. And so we know that we've got density, and at low densities, the regeneration is positive. So as you get more fish, then you get a higher regeneration rate. But at high densities, you get the opposite. And so at high densities, as you get more fish, you get a less regeneration rate due to competition for resources. So there's sort of a resource unlimited part where there's a fast growth, and then a resource limited part where there's slower and slower growth. And that's what drives the S-shaped growth in fisheries without worrying about harvesting or anything. So that's our simple logistic growth model. So if we focus on this curve, we just want to remember this stuff about the slope being negative on this side and positive on this side. This sets up the potentials for some really interesting things as we start adding harvesting into there. So again, I'm just, again, emphasizing this. At high densities, if we think about if you add harvesting, let's say that you're at this density here initially before you add harvesting, and then you harvest more fish. Well, harvesting more fish is going to decrease the density. Well, that's going to increase the regeneration rate. And that increase, because the fish now have more resources, because there's fewer fish competing for them, so they can produce more offspring. So the cool part about this part of the curve is with more harvesting, you get this natural balance where fishing leads to even better conditions for more fishing. So I fish a little bit, and then suddenly the fishery produces even more fish, which opens up opportunity for more people to fish. So it's like if the fishery was producing 5 fish per year, and I fish, as I reduce the number of fish in there, the fishery will now produce 10 fish per year, or to produce 50 fish per year. And so there's more opportunities for more fishing, so long as we stay on this back end of the plot where this slope is negative. Now, what happens when we go a little bit too far? If we bring our density below this critical point here, then now at near this point, this peak, then I might be at a high regeneration rate. But if I fish to the point where I deplete the number of fish in the fishery, that decrease in density is going to make my regeneration rate lower. So if I was almost sustainable here, but just a little bit too much, if I was a little greedy up here, it will lead to a condition where now the fishery can't even produce close to what it was producing up here. And now my little bit of greediness here is going to turn into a lot of greediness here. And if I keep fishing at the same rate, the regeneration of the fish just can't keep up, and the density is going to get lower and lower and lower and drive the fish to extinction. So it's really important in these harvested fisheries to stay on this side of the curve and not on this side of the curve, which we'll see here in a second. So basically what I'm getting at here is that there is this fancy point in the middle that we're going to refer to as a tipping point, and we'll see why we call that. I'm sure you've probably heard about tipping points in your other courses. You've probably heard different definitions of them. We're going to try to give the dynamical characterization of what a tipping point is here today. And so we're going to add, you've already built this model in one of your homeworks where you've got this catch per ship here. And and you've already played a little bit with this because I had you go and figure out, I think, how many ships or maybe what the catch per ship was. I think it is how many ships it was until you actually reach what you're effectively doing is whether you reach this tipping point where you actually hit the point of overfishing. So we can look at that in a little bit more detail. So this is the same model that you built for that homework assignment. And so we start again with the fish at carrying capacity at time 0. And what we're going to do is we're going to let it sit at carrying capacity. And then at this point here, I don't know what that is, 5 years or something like that, we're going to increase the ships at sea to whatever this value is corresponding to 4. I think it's like 10 ships or something like that. And that will simultaneously increase the catch to this level here. So that corresponds to like 250 fish per year or something like that. So now we're fishing 250 fish per year. Now notice what happens to the regeneration rate. The regeneration rate started at 0 because they were at carrying capacity. Fish were just not regenerating. What that means by that is every time a fish would die, you get a fish that was born. So there's no net regeneration. There was no growth in there. So the regeneration rate was 0 because they're at carrying capacity. But now that they've been fished, then the regeneration rate rises. And it's rising because the density of the fish is decreasing. So because the catch is above the regeneration rate, you're gradually reducing the number of fish in the fishery. And that's causing the density to decrease and the regeneration rate to rise. But this process stops when the regeneration rate rises to the catch rate. And at that point, it's a perfect balance again. So we've reached a sustainable outcome. So what do we mean when we look at these graphs about is this sustainable? Well, it's sustainable when the inflow is equal to the outflow, when the harvesting, when the catch is equal to the natural regeneration from this renewable resource. And so we can see that in that the top here, this flattens out. So the fish stock flattens out in these kind of sustainable cases. So because we had so much success increasing the boats there, then we decided to do it again. So we're going to increase the number of ships, and that's going to increase the catch rate. And it happens again. As we increase the catch rate, now the catch rate is above the regeneration rate. So we start removing net removal of fish from the fishery. That's going to reduce the density. As you reduce the density, the regeneration rate goes up until it matches the catch again. And that again is another one of these sustainable outcomes. When they come to a match, then the fish stock levels out and everybody's good. So it seems like this could go on forever. But of course it can't. And so in our next step of this, then we're going to, again, this is kind of, you might see this kind of coming, but this is what's happening to this curve behind the scenes. You start out at one density and fish regenerate at this rate. And so if your harvest rate is exactly that rate, then this population will stay steady. But if your harvest rate increases to a new rate, like up here, it's now above the regeneration rate, and that's going to cause a depletion of fish every year. And that's going to reduce the density. But it eventually rises up and they balance out, and that's what keeps going on. So this is exactly the picture I just showed you, but I'm showing you what's happening behind the scenes to this net regeneration rate curve. Now, if you start catching higher than the maximum possible regeneration rate, so this is the most the fish can regenerate up here, this peak. They can't produce any more fish per year than that peak right there. If you start harvesting more fish than it's physically possible for them to reproduce, then what's going to happen is the density is not going to come up and match and come into balance. It's just going to keep on rolling, and you're going to keep depleting the fish more and more to the point where you get into this bad area over here. So what happens there is the density, if you did exactly this max, they would come into balance. But if you're slightly higher than that, then it's going to, the fish density is going to keep declining. Oh, so that's this way. The fish density will keep declining. And so the regeneration rate will now get farther and farther and farther away from the harvest rate. And as this gap up here gets larger and larger, then you start basically taking out of your savings account balance. You want to spend out of your interest. You don't want to spend out of your principal. And now, basically, the left side of this graph, if we think of the fishery as a bank account, the left side of the graph, under about 50% density, that's principal. The right side of the graph, above 50% density, that's interest. You only want to take out of your interest. If you start taking out of the principal, you're just guaranteeing the account is going to run dry eventually. And that's exactly what will happen here, is that if you keep harvesting at this rate up here, then the density gets lower and lower and lower, and eventually just goes to zero, and then it's impossible to harvest any more fish. So what's interesting is that originally you could harvest here and it was sustainable. But now that your fish are in this regime over here, if you even reduce your number of ships to this previously sustainable level, it is now unsustainable because the fish are on the wrong side of the curve. So here, there's still a gap between the originally sustainable harvest rate and the regeneration rate, which will mean the fish density will still keep declining. And that's what we mean by a tipping point. The dynamics of the system totally change. So whereas things that were sustainable before are unsustainable later. And so that's this tipping point in the case of fisheries, or a lot of these renewable resource systems, we refer to as a maximum sustainable yield. So an MSY, a maximum sustainable yield, how many people have heard about a maximum sustainable yield? Yeah, okay, it's sustainability school, so it's probably like the 5th time you've ever heard this term, but you know, so it, again, just as a reminder, it's the size of the population at which you get its maximum rate of increase. And it's typically roughly half the carrying capacity, because these curves tend to be roughly symmetric. This one isn't quite symmetric, so it's not quite half, but it's roughly half. So it's a little funny. A lot of times people talk about maximum sustainable yield as if it's the thing on the y-axis, when it's actually the thing on the x-axis. It's the density at which you get the maximum regeneration rate. So roughly half the carrying capacity. That's our MSY, and that's the tipping point for this system. Okay, so if I look back now at this curve, at this time trajectory, this behavior over time, then what I see is if I increased my ships more, the catch rate is now way over the maximum catch rate that can be sustainable. It's way over that peak of that curve. And because it's so high, then the regeneration rate tries to rise up to it, but when it hits this point, it can't rise any further. And so we get a collapse in the regeneration rate, which just makes the gap between the harvest rate even larger, which is going to lead to a bigger and bigger collapse in the density. And so that's what we've seen here, is that that even if, like, so this amount of ships, remember back here, the amount of, so this curve here, I'm looking at ships is ship 4. So this level here, this 4, this level of ships and this catch back here was sustainable, but here it's not. So if I reduce my number of ships to this level, it just goes extinct. So in order for me to recover, after I've gone over the tipping point, the only way to recover the fishery really is to stop fishing and then wait for the fishery to regrow and get on the good side of that regeneration curve. That's why tipping points are so scary, is that dynamics that you counted on before the tipping point, you can't count on after the tipping point. And they're really hard to communicate to people, because they'll tell you like, oh, you know, back in my day, we used to do this and we're totally fine. That might have been the case, but it's not your day anymore. And so in this day, it's a different world because you pushed us over the tipping point. So, so that's what this is kind of showing here. All right, so it can't rescue sustainability. We end up just having to stop all activity. That's why we want to avoid tipping points in these sort of contexts. And so again, we're calling this sort of a tipping point. The MSY is the tipping point because the dynamics are totally different when you're in this regime than in this regime. And the only thing you can really do in this regime on the left is stop all your harvesting and wait for natural processes to get you back into this regime. Then you can start harvesting again. All right, so any questions about that example? I think I've got another animation here just to sort of emphasize the maximum regeneration rate there corresponds to this point on the graph, you kind of saw, and that corresponds to this time here. So that's the time at which the system tipped. Okay. Yep. Yep. All right. Okay, so any questions about that example? The slide just tipped. Okay. Questions online? All right, no. Okay, great. All right, so okay, so something that I want to take a little bit of time here is, this sort of system gives us an opportunity to introduce a structure that we often use to summarize these complex dynamical spaces, like how harvest rate relates to sustainability and things like that. And that's this idea of a bifurcation diagram. And so basically what we do with a bifurcation diagram is we take a parameter that we're interested in studying. In this case, it's harvest rate. That's what we put on this x-axis. And then I plot on the y-axis. This is not a behavior over time. This on the y-axis is going to be the steady state value of this dynamical output. So I know that at different harvest rates, there's different transient states that happen, but you know that I eventually settle out, and maybe I settle out and there's no fish in the system at that harvest rate, or I settle out and there's, it's sitting at the carrying capacity or whatever. Whatever it settles out at, that is what I'm going to plot on this y-axis here. So this is kind of what I think I'm going to step through here. So again, this is a parameter that influences the model, but we review it as a constant in the model. So it's not so even though I can adjust a slider, we assume that after I've adjusted the slider, the parameter is not going to change. That's what I mean by parameter. Parameter just means variable in my model that only I, as the simulation god, can change. The simulation itself doesn't ever change that. And then on this side, it's a dynamical variable. This actually does change by the simulation, but I'm interested in its kind of steady state value. So that's what I'm going to plot here. So that's what I'm saying here. So for example, if I look at, for a particular harvest rate, I can look at the net regeneration curve and I can say what densities would balance this system out. So I can say for a given harvest rate, these are the two ways I get a net regeneration that balances this harvest rate out. That's sort of a kind of a, I'll call them sustainable outcomes, but at least outcomes that are balanced. So if the density is here, it produces exactly the same amount of fish for things to sit stable. If it's here, it produces exactly the amount of fish for things to sort of be steady and not moving. So then I have to say there's something special about these two things. Like when I'm at this density, if I were to add one more fish, then suddenly my regeneration rate would be higher than my harvest rate, and my fish population would grow. And so the fish would move away from that point. Likewise, if I were to kill one additional fish just by accident, so there are all these fish that were harvested, and then maybe an eagle, comes in and somehow nabs another fish or something like that. Then now I'm going to have a density that's a little less. So a harvest rate that is going to be greater than my net regeneration rate, and that's going to cause it to run away towards extinction. So this technically is a balance point for the system, but it's what we call an unstable balance point. It's like if I were to take this clicker and try to stick it up on end, if I got it just right, then it would balance, but if you breathed on a little bit, it would fall. But if I hang it down this way, then you could breathe on or whatever, it's always going to come back. So this, when the pendulum is up, that's this position. And as we're going to see in a second, when the pendulum is down, that's this position. So that is what we're going to refer to as unstable, whereas this one over here is stable. So here, if the density is at this point and the harvest rate is there, if you were to reduce the number of fish a little bit, then reducing the number of fish is going to increase the regeneration rate, which is going to cause them to quickly replace the fish that was reduced, and it comes right back to that point. If you were to add a fish, you just would dump more fish into there, that's going to cause the regeneration rate to decrease, so that now the harvest rate will be greater than the regeneration rate, causing the fish population to go back towards it. So this one always kind of comes back, and that's why we refer to that as stable. So that's stable, and that's unstable. And then the last one we have to worry about is the extinction point. So if I actually have no fish in the system, then if I were to add a fish, the regeneration rate's way lower than the harvest rate. So it goes right back to the unstable point, or to the extinction point. So the extinction is stable. this point up here is stable, and that one there is unstable. So there's 3 possible steady state outcomes for this harvest rate. Okay, so, and that's kind of summarized here. Stable, stable, unstable. Does that make sense for this harvest rate? Okay, I can summarize that into stable, unstable. So I can summarize that by putting them on a curve, and I can basically take this regeneration curve and kind of flip it so that that exercise that we just did is kind of, it's turned on its side, but it's exactly the same thing here, where now the regeneration curve, and this is scaled a little funny, but imagine this was sort of stretched out so that this thing was sitting on top of that. I'm not sure why it's duplicated right now, but basically we've just got this regeneration curve, and I've just put it on its side. I kind of flipped it around so that for every harvest rate, I can look up these possibly 3 points. And so this tells me, if I were to sort of get rid of some of this stuff here, this extinction equilibrium is always stable. So if you empty out the fishery, it'll stay empty forever. And if you add 1 fish to it, then for pretty much every harvest rate, it's going to go back to being extinct. And the solid line up here, these represent sustainable fish outcomes. And they're separated by this unsustainable ones from here. So what we're saying here is that low harvest rates, then so long as you're above the dashed line, then if you're far enough above the dashed line, your system is going to come to this point up here. It's going to sit at one of these sustainable ones. But if you push the harvest rate so far, the dashed line isn't there to prevent, basically you can't cross the dashed line. The dashed line's like a fence. Because it's unstable, everything runs away from the dashed line. It's like the peak of a hill, and you've got to run up the hill to get over it. And if you just don't have enough energy to go over the hill, then you're going to stay on this side of the hill, in this valley. So it's like you got a valley here, and a big crest of a hill here. And as long as you start on this side of the hill, you're never getting to the other side of the hill. But if your harvest rate gets large enough, the hill goes away. And now at that point, when you're in this harvest rate, you pretty much, you're going to naturally roll over to this valley over here. And at that point, the only way to get back is to reduce your harvest rate, super far. Like you're pretty much, in this region here, you're stuck kind of going to extinction. So, I can play this little game here with this bifurcation diagram. So again, I'm just saying, in this region, you attract towards that side of the hill. In this region, you attract towards this side of the hill. So we can imagine, and so we refer to this as the sustainable region. So for these fish populations, these are the harvest rates that are sustainable. So the higher you start in fish population, the greater the harvest rate you have until it's sustainable. But there is a critical harvest rate in which the harvest rate's always unsustainable. And for low populations, then there are fewer harvest rates that are sustainable. And that's what this is communicating here. So we can play kind of and that's the tipping point is depicted there. So if I've got sort of an animation where imagine I start here at this sustainable point. So this harvest rate, my population started high and I chose this harvest rate. Well, if I over harvest, then I'm now in this unsustainable region where the system is going to move toward extinction. And so my only choice is to reduce my harvest rate. But because it's declined so far, if I reduce my harvest rate to my previous harvest rate, there's no way I can get back there. So what I'd have to do is reduce my harvest rate even farther to get back into the blue region. And once it's in the blue region, it will go back up. And then now I can go back to harvesting like I did before. So that's what these bifurcation diagrams help us think about, is it helps us summarize for every single harvest rate. It's kind of the relationship between the harvest rate and the history of the fish population. So it helps us figure out, these sorts of points. And when you have these folds like this, that indicates that you have a tipping point in the system, which are really scary, and you want to try to avoid getting close to. So then it goes back around here. And this characteristic where you've got kind of this small change in harvest rate then requires a large change in harvest rate to get back, that's what we refer to as hysteresis. And so hysteresis is a term that means that the history of a system determines whether a parameter, the thresholds for parameters. So we, in like normal mental models, we might imagine there is a single, harvest rate that determines sustainable or unsustainable. But what we're saying is at high populations, then there's one harvest rate that separates you from unsustainable to sustainable. But then at low populations, there's a totally different threshold. So I can fish a lot when I'm at high populations, but if I let the population get low, then I have to back my harvest rate way off, way below I did there. And that path dependence is what we refer to as hysteresis. Yeah.
In the hysteresis, how do you read where you need the fish to make it more sustainable again? You've already processed it.
You would refer to that. So if the population was here, right, then it would be back to the dashed line. So you draw it straight horizontal. Right. In reality, I mean, this, if we're talking about the dynamics of this whole thing, it's going to take time. Like if you, immediately snap your harvest rate back to here, there may still be some residual, inertia as the system comes down. So, so you might think that you can reduce your harvest rate here, but really you should probably go here to be safe. Because you could kind of imagine not like a straight trajectory, like this population could kind of go this direction. So these bifurcation diagrams are really meant to be a static snapshot of what's going on now, but then we can use them as a mental heuristic for how we recover these systems. All right. So any questions about this bifurcation diagram? It's just mapping out all the stable points and a parameter of interest. Okay. All right, so summarizing all this stuff up. So these tipping points, so again, you guys have already heard tipping points, you probably heard all the analogies. This is my analogy. I think about a refrigerator or a large rectangular, heavy rectangular object. The rectangular is kind of important. It's sitting at a ground position. Imagine that you put a little ramp underneath it, so you caused it to tip a little bit, but it's still stable. It still stays upright right there. And what I mean by that is if I bumped it just a little bit, if I move it just a little, then maybe I'll go back here. If I were to just bump it just a little bit on the side here, if I just sort of kind of like, hit it a little bit, as long as I didn't push it too hard, it would wobble a little bit, but it would come right back to this position. Now, eventually I get to this point where the center of mass is right over the corner of the refrigerator. And this is the so-called tipping point. So this is the point where if I were to bump it a little bit, it will come back to a stable position, but it won't be this stable position. If I were to bump it a little bit, it will tip over. And this is a new stable equilibrium for the system. And so this is probably not a good operational mode for the refrigerator. Now, naively, I would think, well, I just need to get rid of this angle. I'm just going to go back to the original angle that the refrigerator was happy with. But it doesn't set itself upright again. In order for me to set itself upright again, I actually have to go farther in that direction. And so I have to tip it farther out this way so that it flips over. And then finally, it's back up there. So that's where the term tipping point comes over. It's actually, I think, a glass of wine is actually where they came up with it. I think I have a picture of that. So I think physicists thought about a glass of wine, and they said, there's a particular point where the glass will tip, and the glass of wine is even more dramatic because then the wine spills. And even if you can manage to get the wine upright again, you can't get the wine back in the glass. So that's like a totally irreversible tipping point. There's no recovering from that. So that's where the term comes from, thinking about a glass of wine. And there are a bunch of systems that potentially have these tipping points, some that claim to have already been tipped and some not. And so if we think about these in terms of like ice sheets and so on and so forth, there's a lot of logic out there that says, well, we can over-consume or over-produce emissions or whatever now, because maybe later we can just back off to levels where we were fine before. But the worry is if you go so far, if you melt all the ice, for example, in the ice caps, even if you go back to normal temperatures, it's not going to all go back. That ice now is like wine that's been spilled out of the glass. It's now in the ocean, right? So, so there can be irreversible points where if you go too far, you can't ever go back. And that's the scariness about tipping points. But when we think about tipping points, there's also, so there's bad things like climate change. There's also political instability. So, how much can you screw over your citizens until they decide it's enough? So you could say, I'm gonna, whatever, tax you, or murder you, or whatever. Eventually there's enough, right? Eventually there's a point where you could say, no more murder, we're going to go and overthrow this government. And at the point where they realize you're about to overthrow them, they could say, all right, sorry, no more murder. But if you've already brought your population to the point of rebellion, you probably can't just say, take backseas and hope that they'll just stop, right? They've reached a tipping point. So that's another way we can apply this. But this also can go in good ways too. So there can be, like you can put out advertisements to tell people to, recycle. And you could say it takes us millions of dollars to get people to be convinced that they need to recycle. So, if we depend on advertising to keep people recycling, we're going to go broke. But if you can manage to get people to switch their norms, their expectations, then once they've established a pattern of behavior, you can back off the advertising. And even though in the past you didn't advertise and no one recycled, now when you're not advertising, people are recycling. So that's an example of a good tipping point. So tipping points are really important when thinking not only about physical systems, but certainly about social systems as well. And they're very popular. People write books and make lots of money. So it's good to know the terms. So, all right. Any questions about tipping points? Questions online? Okay. All right. So the last thing I want to cover today is something I hope will be useful when thinking about feedbacks in your final projects. And what I really like about this chapter is they close the loop and they actually implement policy and reactions from industry to policy when thinking about a fishery. So now we've got a regulated fishery is what we're modeling here. So how do we do that? So the first thing we have to do is not only model how fish grow, but how ships grow. So before we had a slider and we chose how many ships were out there. We now want to get rid of that slider and let the system decide how many ships to put out there based on the background context. So we've got our ships at sea, and because now this is changing over time, we make it a stock. So it was a slider, now it's a stock, because we want it to be able to change over time. And things that change over time on their own are stocks. The things that make stocks change are flows. And what is the thing that makes ships at sea change? It's the purchase or sale of ships at sea. So they show this as a bidirectional flow. It can go in and out. You could have also made this a unidirectional where purchase goes in and sale goes out. They just combined it all into one. That's fine. And so the way they modeled it is a little bit like the toilet tank model. So that's the reason why I gave you the toilet tank model, is that feedback system keeps coming back over and over again. And they basically have a desired fleet size down here. And that desired fleet size, like the 15 centimeters in the toilet model. Now there's a propensity for growth factor they put in here. So they actually allow the desired fleet size itself to change. It's like the water level in the tank to move up and down. But basically once you've got it, then you compare that desired fleet size to your actual fleet size. That produces a gap, just like the tank gap. And that tank gap goes in to this purchase, but then you divide the tank gap by the time to adjust fleet. This is the toilet model over and over and over again. You're just dividing a gap by a time constant. And that's how we model ships. And if the ships are over the desired fleet size, they'll come back down to it. If they're under the desired fleet size, they'll come back up to it. And the rate at which they do that is going to be set by this time to adjust fleet. So that's how we model changes in the fleet. So how do we do this propensity for growth? So they've implemented this kind of slider method here, where they have a normal propensity for growth, which you can set yourself. That's your exogenous variable, or you can just leave it constant. And then there's this propensity of growth, which I think I'm going to zoom in here. There's this effect of fish density on catch per ship. So this is a lookup table, which as the fish density changes, the individuals on the ships notice that they catch more or less fish. So that's going to be an important feedback, because then that's going to affect, the catch per ship, and that catch per ship is going to go into another lookup table modeling the kind of psychology here, where based on their current amount of catch, that's going to affect how much they're going to modulate their propensity for growth. So if they're getting a lot of catch, they're going to go above maybe the normal propensity for growth. If they're getting low catch, they might go lower than the normal propensity for growth. So we're modeling the kind of psychology of those doing the fishing based on how much they're actually catching. And that's going to change their propensity for growth, which will end up changing the number of fish or the number of ships that are at sea. I think this is me just stepping through those steps here. So basically, I could summarize that whole thing in this balancing feedback loop, where the fish density, if you increase fish density, you increase catch per ship, which will increase their propensity for growth, which will increase the ships at sea. But that ultimately will eventually reduce the fish density, which will cause it to reduce the catch per ship, which will end up causing the propensity of growth to kind of level out or even decline if they've reached the tipping point and the fisheries collapse. So this is a mechanism that we can use to actually regulate the number of ships at sea based on the current density of fish, so that we can close the loop and let the system run without regulation. And that's what we've got here. So we've taken something that was a slider and we've turned it into a two-sector feedback model where the fish grow, and then after the fish grow, the ships grow, and the number of ships that grow affect the number of fish, and the number of fish that are available affect the number of ships that grow. This is a little bit like the water model that you guys did for assignment E5, where you've got a population that's growing here, and you've got a resource over here that's affecting the population growth, and they kind of affect each other in this sort of two-sector model. So that's an example of how you can actually model the human behavior in response to the behavior here. You guys in the back, it's a little distracting for me. I appreciate that they're talking and everything, but yeah, I mean, if you need to, you can step out outside, and that's fine. All right, so that's what we're trying to do. We call this making the. Is there a question online? If not, okay. All right, so what we refer to this is we've made this shipping investment decisions endogenous to the model. So before it was a slider, anything that's a slider is exogenous. We don't know how it's set. You set it as the model builder. Anything that's determined internally in the model is endogenous. So we've made this an endogenous investment model here. And so what happens with this is we now can see the ships at sea, this was 4 here, it actually has a bunch of cool dynamics by itself. So this curve in 4 is not generated by us, the modeler, adjusting a slider. It's actually adjusted inside the model by the density of fish. And so at this time period here, I think at this point they adjust the propensity for growth or something like that. But then after that point here, this is all endogenous to the model. And so the idea here is the new fish per year is stable, but as the ships at sea grows, because they are getting a lot of catch, so their catch is this line 3, because their catch is high, their growth grows, which is going to increase their catch, but eventually they're going to reach this point, the tipping point here, where the new fish per year collapses. Now, they don't realize that the new fish per year has collapsed because they're able to continue to get catch. And so because the catch is high, they continue investing in more ships. Now, eventually we get to a point where their catch is so much higher than the regeneration rate that the fish stock collapses to a point where it starts making a dent on their catch. And that's what happens kind of up here. So when this collapses really far, it starts making a dent on their catch. And at that point, they start bringing ships out of the fishery, but they bring them out way too slowly and the fishery goes to extinction. So we've actually modeled an entire extinction event in the sim. So we've closed that loop where we can actually start studying when do policies actually lead to extinction and when do they not? What sort of human behaviors lead to extinction and what do they not? So it's actually good that we got a collapse here because that actually matches what would happen in a real fishery. So this becomes a useful surrogate model. It's not just sliders that we can kind of play around with arbitrarily. So the other thing that this thing does then, which we're probably not gonna have a whole lot of time to talk about here, but just to give you an idea of the rest of what's going on here, is that in order to really, we need a third sector in order to really model policy intervention in this case. And the way we do that is we basically have to have a model of scientific information, so an estimate of fish density. So there's going to be a true fish density, an estimate of fish density, which won't necessarily be the true fish density, and I thought, you know, an idea of an optimal fish density, and then policies which try to encourage those in the industry to change their ships at sea to try to help us hit this optimal fish density. And so they end up building that in Morecroft, and I don't want to go through all of the details here. I think I might step through this in more detail, but basically this is the same fishery model we had before. This isn't that different than the ships model, except they have a ships at sea as well as ships in harbor. And so there's this age structured population down here of whether your ships are out, whether they're in harbor, or whether they've actually been scrapped. And but then the big thing that they've added is this policy angle here, where they estimate the fish density and they try to come up with a sustainability index, which changes their recommended ships at sea. These are all things you can experiment with to say, at what optimal fish density do we manage to keep this fishery sustainable by use of policy? And at what points does policy not do that?
So much a man can do.
So
I just gotta go to the
I just need to mute while I finish up this.
Nah, just my work shoes. I literally didn't even go back to home. I work at a True Shot Gun Club, and
Well, I think
so
I can
like
listen to this conversation about work shoes while I do this.
cool. Fine.
So
You guys need somewhere to work though.
So you have to bundle in all that policy stuff into ship operations and the human behavior, and basically we're just adding in more coordinating networks, which have the feedbacks from the policy that are trying to change the propensity for growth. And so with just sort of going through all the sectors, I put all of that together, and I'm not going to go through all these details. Then what we basically had is we can have a policy arm
Like dots and shit. Well, it's
different investment behaviors,
yeah, it's just like
and that allows
spread
us
down
to
the
play
sides.
with
I was
things
worried about
like
it 'cause it hurt.
target
And
fish
so, but
densities
now,
in the policy. That allows us to, as we switch that back and forth, then we can see kind of like in the oil producer model, oscillations come into play, and those oscillations are generated by being over our critical fish, our optimal fish density, or under our optimal fish density, back and forth. So we can see regulation kicking in and then letting off, and kicking in and letting off. And it looks ugly, but the nice thing about it is our fish stock doesn't ever hit zero. So we managed to simulate a case where we don't get extinction. And if we make our target density significantly higher than the maximum sustainable yield, then we don't get into as many of these danger zones that lead to these oscillations. So even though the maximum sustainable yield might seem like an economically favorable place to put things, by actually making our density a little higher than that, we add a safety margin and we don't get these huge oscillations. So
Pam doesn't even drink.
So basically, these
Alyssa, finish your
experiments
drink.
allow us to see whether we can rescue sustainability and how ugly the solution will be, because people don't like things when things oscillate here. So sometimes actually adding more regulation softens these oscillations. That's one of the things that we kind of learned. So in some cases you get these. So these are different scenarios where changing the compliance rate and so on can change those sorts of oscillations. But the big point that I'm trying to get here is that regulation tends to add oscillations. And what we can play with in sim is how to sort of damp those oscillations And what would happen if, for example, it got more efficient, if it got easier to buy and sell ships, so not make the oscillations worse,
No worries.
better, and so on. So that's kind of how the chapter ended. So, so before I do that, so I would just, before I ask for any questions, I don't want to go over here. So just remember our last chapter of the book. So the last reading assignment is due Tuesday, I guess. So over the weekend, there's a muddiest point. So there's perusal for that sort of stuff. And that's pretty much it. So I'll give you an attendance question. And then if you have any questions for me, I'm happy to take them. Otherwise, you can get out of here. So for those online, there's the URL. And the question here is, what does MSY stand for? So what does MSY stand for in terms of, say, renewable natural resources? And with that, that's all I've got for you. So mute.
Does Vincent have the ability to do bidirectional flows?
Yes, yes. I don't think you have to check anything on and off. I was trying to think if Vince, yeah, I think because sometimes in some programs when you turn it on, it like adds a double arrow, an arrow on one side and the other. And I think Vincent just always has bidirectional flows turned on, unless you selectively say turn them off.
Oh, I think you're right, actually.
Yeah.
I think when you draw a flow, it has the arrow inside it is bidirectional.
Okay, that might be the, yeah, I just don't remember off the top of my head, but you definitely can do bidirectional. Yeah. Hold on a second. I'm going to go ahead and end the recording. So for those online, that's all I've got for you. I'm going to go ahead and end the recording.